So the biggest open question in terms of hyperbolic cones is whether all hyperbolic cones are all hyperbolic cones are spectrahedral. So meaning that they correspond to a hyperbolic polynomial of that form. So that there exist matrices of a certain size such that the sum, so this is from 1 to n, and these matrices can be of any size, such that that cone can be represented as the hyperbolic cone of such a polynomial. So that's known as the, so this is the generalized Lax conjecture, and it's called generalized because the Lax conjecture was the case in which n is equal to 3, and that's solved. So that's due to Helton and Vinnikov and seven, and then also those Parillo and Ramana. The case in which d is equal to 2, so the case in which the polynomials are quadratics is also solved, and so that's due to Netzer and Tom. And there's a few other cases which are known. So for example, in the case of the elementary symmetric functions, so that's a result of Brandon. Uh, 2014, and so the question is whether all hyperbolic cones can be represented in that way. There is also a so it's not clear whether hyperbolic optimization goes beyond that setting, which but still it's an interesting, it's in terms of efficiency, it's actually quite interesting, because there is the question of the representation. So I haven't, of the dimension, so I haven't discussed algorithms, but one thing that's nice about hyperbolic optimization, and maybe I should have said that earlier, maybe I'll change, maybe I'll give one or two easy exercises now, and then I'll get more time at the end. So as an easy exercise, okay, let me give you an easy exercise. An easy exercise is to show that if you look at the elementary symmetric function sigma n minus 1, so that's of x, so you're taking the product of all the monomials involving n minus 1 of the n variables, that's indeed spectrahedral. Any idea how to do that? So we're looking at so sigma n minus 1 of x is the sum over I 1 to n of the product over j between I of xj. And so I want to represent the corresponding convex cone as a spectrohedron cone. So in that form. So far I haven't given you many techniques. The only thing I have given you is the fact that if you take the spanning tree polynomial of a graph, or more generally, if I give you a regular matroid, and I look at the basis of that regular matroid, that it has a spectrohedron representation. So the guess would be that
take the spanning tree polynomial of a cycle.
So if I take the spanning tree polynomial of a cycle, indeed that's that corresponds to this. So spanning tree. So this is the spanning tree polynomial of a cycle. So now you could try. So if you want to prove this result of Brandon, you could try. You might say, well, maybe you could show that it's directly the so spanning tree polynomial of a graph, or maybe you could show that. If you look at, so if I look at, for example, sigma I could hope that this is the polynomial corresponding to a regular matroid. But unfortunately, that's not true. So this corresponds to the matroid, which is a uniform matroid. On n elements, and you take every subset of size I, but even the U2 form is actually not regular. And this is easy to see. In fact, U2 form is so so it's actually not even binary, and to be regular you have to be representable over every field. So that's the two element. By binary I mean that representable over the two element field, and so and another, I mean, but you can view directly that U2 form is not regular, because if there was a totally unimodular matrix that corresponds to it, you could assume that the first two columns, so you have to have 4 columns. And so when you have a representation of a matroid over some field, you can always assume that you have an identity matrix. You can eliminate some rows, and you can assume that you have an identity matrix. And so it's just the rest that you have to, but you have to make sure that every 2 columns would be independent. And so for this column and that column to be independent, this has to be non-zero. For this column and that column to be independent, no, it's just the opposite. This one has to be non-zero, and this one has to be non-zero for these two. And similarly here and there. Now, to be totally unimodular, you would need this to be 1 or minus 1 each. So this is plus minus 1, plus minus 1, plus minus 1, plus minus 1. But these two columns should be independent, so one cannot be the minus the other one, and you can choose by basic operations, you can choose the sign. So you could assume that this is 1 and 1, for example, and this is 1 and minus 1. But that's not totally in modulo because the determinant of this is 2. So U2 form is not, it's not regular. The same argument shows you that it's not binary. And so you can't use that Cauchy-Binet formula to get this. So you need to work more form to get a result like this. Now, again, this is what's one key fact here is that you might say, but you said so one thing that you should realize is the following: is that what are operations that maintain hyperbolicity? So if I have two polynomials, P and Q, that are hyperbolic in direction E, then if I take Px times Qx, it's also going to be hyperbolic in direction E. But what happens is that what is the cone corresponding to this? So the cone corresponding to P, the cone corresponding to Px Qx, it's going, so one way to look at it is that it's going to be the component that contains E when I remove the zeros of this. So that's going to be the cone corresponding to P intersected with a cone corresponding to Q. So in particular, if let's say, if K plus Px contains, let's say, is contained in Q plus Qx, that means that this is just K plus of Px. So that means that I have another hyperbolic polynomial that represents the same cone. So what happens is that when I give you the cone, I don't necessarily give you the polynomial that corresponds to it. So there might be, so this is one polynomial, but you might be able to multiply it by another hyperbolic polynomial whose cone contains the cone of elementary functions, elementary symmetric functions, and get a spectroidal representation of it. So that's something that's important to realize.
So am I right that the related question, the answer is going to be negative, right? That not every hyperbolic polynomial can be written in this form.
Yes, that's, so yeah. No, right? Yeah, right, exactly. So so it's really for the cones.
Right, okay.
Not for the polynomials. Yeah, exactly. That's it's a good point to emphasize.
So can the elementary symmetric functions be written in that form?
Yeah, that's
yes. Yeah, that's a result of
so is there an example of a polynomial which is not determinantal yet whose cone is a spectrohedral cone?
Yes. For example, this one. So the elementary symmetric function. So you ask for.
I'm asking for a polynomial,
yeah.
a hyperbolic polynomial, which is not a determinantal polynomial. So it cannot be written, but its cone
right.
is spectrohedral.
Exactly. So this one for I not equal to n minus 1 and not 1 cannot be represented. I mean, but it is spectral. The corresponding cone is spectroidron.
Oh, but not being represented is a stronger condition than being determinantal, right? Or no?
So you cannot write this as that for I not equal to the extreme cases. Let me, because I realize I haven't said much about why. So, yeah.
One question. So I know that the elementary symmetric polynomial can be written as a, like the cone can be written as a determinantal, but when you blow up the number of variables by a square, I think that's the result of Pablo.
Right. So the one thing that I'm not discussing is that so by spectrohedron I mean the cone corresponding to this. There are also shadows of these spectrohedron, and so the result of Pablo Parillo and Sanderson is about shadows of such things. So this, because this result of Peter and Brandon, the size the size of these matrices are something like n to the I or something, right?
Yeah.
N to the I, while so what Parillo and Sanderson show is that you can get them as a shadow of just quadratic size.
Any hyperbolic is a shadow of...
No. They show that the elementary symmetric functions can be that the hyperbolic cone corresponding to it can be viewed as a shadow of a spectrohedron corresponding to matrices of size quadratic.
Is it known that...
What is a shadow? Sorry.
A projection, I guess.
It's a projection.
Yeah, is
Projection.
it known that every hyperbolic cone is a projection of something spectrohedral, or is... It's known.
It's known for smooth.
Right, smooth, yeah.
How smooth? C2?
Gradient on zero and it's n over t because it's
But so my question was that, so yeah, my question is that how do we know about the blow up? So, like, I know for this there's a square blow up. Do we have some?
So there are no, so essentially,
I know there are no.
so in terms of projections, then there are some results. But in terms of, if you just look at the size of these, it's actually, to the best of my knowledge, that's completely open what the size might be.
But for shadows, I don't think it is a polynomial bound.
No, it's not all. No, it's not known to be always a polynomial bound. No, definitely not.
Candidates. So I was looking for, is there some interesting class of polynomials that we can study this? Like,
so for example, I can tell you, one of my favorite questions is the following. So that I told you that all polyhedron cones are hyperbolic because they. So if I have p of x, which is just the product of a bunch of linear functions, that's hyperbolic. But I'd love to, but there could be, so this could be an exponential number of terms. So for example, if I look at, let me take a graph and let me look at the matchings, all the matchings in the graph, in graph G, and let me look at the polynomial that corresponds to the conic hull of the matchings in the graph. So what I'm going to look at is, let's say, the product, for example, let's say over all sets S of vertices S odd of maybe x naught times S minus 1 over 2 minus the sum over the edges within S of xc. So if I take this exponential number of linear functions, so these are functions in terms of the edges of the graph plus one variable to homogenize it. So that cone corresponds to if you look at the matching polytope, you have one facet for each facet of the matching polytope. I have one such inequality. Now that's hyperbolic, but it's known that if you try to view that as the projection of a polyhedral cone, you still need an exponential number of inequalities. That's a result of Thomas Rosworth. But you might be able to represent it as a, for example, as either a projection or of a spectrohedron cone. And why do I care about this? It's partly because, and I guess so I'm a bit confused by the schedule because I've been a bit. Should I at some point stop a bit and
Stop for like 15 minutes.
At some point I should stop for 15 minutes. Okay, good. But let me say one thing that I find. So you might say, okay, fine, you defined hyperbolic optimization as minimizing Cx, subject to, let's say, Ax is equal to B, and X is in this hyperbolic cone. But why is that? I mean, for many cases, is that easy to? I mean, it has some easy special cases like linear programming, semi-definite programming, but it's actually it's often easy to optimize over this, and it's simply because one can show that if I look at minus the log of p of x, so I have k plus plus, and I know that k plus plus is the component of Rn minus p of x is equal to 0 that contains the hyperbolic direction E. And so minus log of p of x is a function that actually goes to infinity as you approach the boundary. But that's a baryon function. So for people doing convex optimization, they like to have a baryon function that's a function that's smooth and well behaved, and that goes to infinity as you go towards the boundary of the set, and that has some additional nice property. And so one interesting property of this is that the fact that p of x is a polynomial means that if you look at the derivatives of that baryon function along any line, you can relate the first derivative to the second derivative and the third derivative. They are reasonably well behaved. And so in particular, one can show, and I think this was probably first observed by Guler, can show that minus log of p of x is a self-concordant baryon function and self-concordant functions come with the parameters, which gives you the complexity. But the parameter in this case is the degree of the polynomial with parameter d, for any for any hyperbolic polynomial D, polynomial P. So this means that, so this notion of self-concordant function, I can define it if you'd like, but so this was a notion that was introduced by Nesterov and Nemirovsky. And it was introduced to show that, to see what you need, what kind of properties you need for the baryon function, so that Newton's method converges quickly. And indeed, once it is self-concordant, you can use Newton's method and it will converge quickly to an approximately optimal solution to this optimization problem. So, so what it means is that if you have a hyperbolic optimization problems for which you can evaluate P of x, then you can actually efficiently, so if you can evaluate, so if one can evaluate P of x efficiently, one can optimize up to epsilon efficiently over these over ax is equal to b, x in p plus plus. And so, I mean, unfortunately, when you have, let's say, a function like this that has an exponential number of terms, it's not clear how to evaluate that. So you need to find hyperbolic polynomials that you can evaluate efficiently that gives you the same hyperbolic cone that you're interested in.
So in this case, there is no hardness. I mean, we can test if this is positive or negative. Like if all of these are non-negative, right? All of the terms.
Yeah.
But you don't know if we can evaluate.
Not to my knowledge. Yeah.
And if we can just use the interior point method. So
yeah. If we could evaluate that, yes, exactly. Yeah. Because I mean, I said that you need to evaluate P of x. There is also, and maybe I've lost the time of the schedule. Maybe I'll get back to it. But so supposedly for Newton's method, you have to evaluate not just the baryon function, but you have to be able to evaluate also gradient and Hessians. The fact that so Reneghan, for example, showed that the fact that you can evaluate the function and that's a polynomial means that by interpolation you can easily evaluate the gradient and the Hessian. At least if it is exact, it's easy. If it is non-exact, I don't quite know.
I think non-exactly you can kind of do it if you know how far the roots from zero.
Yeah. So, but I don't know if
within an additive error epsilon.
Yeah, I don't know.
Probably not good enough, right?
I don't know if it is good enough. I presume it's not good enough. Should I pause for 15 minutes and then start again? Yeah. Okay. Sorry for these.